So today I will talk about how to build fantastic machine learning applications. All of you or some of you are building machine learning stacks at your companies, same as we do at Salesforce. OK, I'll try to speak closer to the microphone. Is it better? So I would like to start from a quote. This lonely scene, the galaxies like dust, is what most of the space looks like. This emptiness is normal. The richness of our own neighborhood is the exception. Let's take a moment and appreciate our habitat. We're actually really lucky that we have such a rich world around us, especially as we have so much interactions and data and things happening and we keep exploring. So this quote actually comes from a documentary I watched a while ago called Powers of 10. And in this little documentary, it's like a 10-minute video that travels from our habitat, like starts from 10 to 0 and zooms out to the observable universe, and then zooms in back to the level of quark. And it kind of gives a great perspective of how vast the world is. Gives an understanding what actually the power of numbers and the size of the universe. I'd like to draw an analogy, similar analogy, with the machine learning. When we build machine learning applications, we have a lot of levels of complexity that we have to go through, that we have to cope with. We start from data collection, where we have to identify which data sources, what kind of data we need to collect. Then how do we store it? Then we think about how we prepare this data for different machine learning use cases. And eventually, we get to the feature engineering aspect of it. After that, we have much more levels to go through, right? When we engineer features, we want to select what are the best features that maybe make our models faster and performant. We think about sampling. We think about different algorithm implementations. Some of them are already there, some of them are not, and so on. Right? For each algorithm, we might have a lot of parameters to tune, and we have to think about all of these little things and experiment with them. This creates a lot of complexity for us. This is by no means an exhaustive list, so you can add more things there. For example, benchmarking or model quality, how you guarantee it across different deployments when we roll out models. So I would like to ask you a question. How long does it take for you guys to build a machine learning application? Is it hours? I don't see much hands here. Days? Like maybe here weeks, months, or maybe more? What do you guys think? It's more? So on average, it takes months. It's like this. So this picture is like a black hole. It's like a black hole that sucks all our time. It takes all the time of all our teams and just sucks it in. We start experimenting. We start tuning arguments, parameters. I'm not even talking about the deployments, right? It's like Hadoop parameters or Spark parameters. So how do we cope with this complexity? Is there like a magical formula or maybe some magical method that allows us to deal with this stack of problems that we have, so we can actually make it hours? We actually want to shrink from months to hours. We don't want to spend much time. We want to experiment faster and move faster with our theories, right? Because when we build machine learning applications, we actually make a theory, and then we want either prove or disprove it by proving the correctness of the model. Usually we disprove it and we move on, but this experimentation has to happen faster. So as a software engineer, we all know, so the task of the software development team is to engineer the illusion of simplicity. We want to make it simpler to work with complexity without too much hassle. So I'm, as a software engineer, this is my main challenge when I build machine learning applications, is how to make sure my team is successful and my company is successful eventually. So what does it mean, right? So how do we engineer this illusion? We build abstractions. We build we just layer complexity in these boxes of abstraction, right? It's from left to right. Let's look on this image, right, of bears in the woods. It's like a Russian painter. You see a lot of details, but what we really want to see here is that, okay, some there's a beautiful morning in the forest, and bears are just naturally behave the way they do, and then we can enjoy this. And then moving to the right, the level of abstraction increases, and we might think of our system as a black box, right? And it's not that useful to think about systems as a black box because they might not be then applicable well in different scenarios. So to cope with complexity, we need to find some proper level of abstraction, the way we can easily argue between ourselves and within our teams. So it actually boils down to a simpler problem. Well, it's not that simple, but it's at least I can explain it in one slide. How do we find an appropriate level of abstraction to deal with those machine learning problems, as I mentioned, feature engineering, feature selection, and so on. When we talk about abstraction, right, especially in software, we're really talking about language. So how do we express our thoughts when we talk to a machine, when we write out the requirements for the application? So language syntax and semantics, they define the degrees of freedom of the engineers, of the teams, the way we express ourselves. So if we like look on the two parts of the spectrum, the higher degrees of freedom are, we get basically lower abstraction. Think about language as C or assembler. It's suitable for much more complex problems. It's more difficult to use, right? And it's error prone. Why? Because we have to repeat ourselves every time we do some relatively simple operation. There's like we can barely reuse some of the stuff. We'll have to work around it. With a higher abstraction, such as maybe you can think of maybe higher level DSL languages, and even SQL actually is a good example, right? It might be less flexible, but it has much simpler syntax to remember. The learning curve is less, and then we get a better reuse of the functionality that we do. So similar to machine learning, right? We think of a higher level concepts, maybe like TF-IDF, or one-hot encoding, or we talk about some algorithms. We're going to do logistic regression, linear regression. These things, we can write them down in one word. We don't have to write the for loops every time. So there's another quote I'd like to mention from Martin Odersky that says, functional programming removes one important dimension of complexity. To understand a program part, a function, you need no longer account for the possible histories of executions that can lead to that program part. So this is very important to us because, well, not to us, I think to us as a humanity, I guess, to understand the importance of functional programming is that we can argue faster on the library and application development as we go. So if we use this ability of functional programming, this property of functional programming, and apply it to build machine learning application, I think we can get to a higher success here. So in the functional approach, right, I kind of wanted to mention like top 5 probably perks that we get, right? Everything becomes type safe. We don't see any side effects when we look on a function. We get better composability, and the syntax is very concise, fine-grained control as well. So we get, so just in this example on the right, this is an actual code from our code base. Maybe I would like to extract some features from the URL, and I would literally write a couple lines of code here. Okay, I'll just create a URL. I don't think of exceptions because there are no exceptions. It's all properly safe. And I only think about the input and output types of this function. And then I can use it to map over values very easily. So going forward, right, we also know that there is another approach, right, object-oriented approach, where we get 3 more perks of modularity, code reuse, and polymorphism, which are also extremely important when implementing data-rich functionality as we require for machine learning when we deal with different types of data and operate on different inputs. So in this example on the right, I also kind of explain what it means, right? So I'm just showing some polymorphic properties of a tokenized function. Let's say I have a sequence of some values and I would like to tokenize So depending on the type, they will tokenize differently. In this case, base 64 encoded string will be first, for example, decoded and then tokenized. And maybe for phone numbers, the phone number will be parsed correctly. And if it's an incorrect phone number, I might get some other sane default that won't make my machine learning pipeline break. So, which actually leads us to the next slide, which contains like a little why Scala. Yeah, so we actually like Scala and we use it all around our stack because it combines all those things I mentioned before, as functional approach and object-oriented approach. It's a strongly typed language, and it allows us to build very concise language to cope with the complexity of machine learning flows. It's mostly fun, unless you hit some dark corners, which we try to avoid. And then it's just a joy language to use. And of course, it's default to Spark, which allows us to scale our pipelines without rewriting the code base after experimentations. Like our data scientists actually experiment in Scala and Spark directly. They don't do R models and then we rewrite them. It's not what we're doing. So we actually went ahead and we developed a small library to allow us to cope with this complexity and like make it much nicer to deal with the feature engineering, feature selection, model selection, and so on. So it's an AutoML library that we call Optimus Prime. It provides us very declarative and intuitive syntax to work with machine learning. What I like the most is like it gives us very high accuracy with a significant reduction in development time. When I mean development time, it's actually prototyping phase, proving disproving theories, and then also deployment to production. All those cycles we try to cover within one framework. So just to give you like an example of what actually Optimus Prime contains, right? So it might look as simple, but it's actually underneath. We had to build a lot of types. So this is like one example of our type hierarchy that the part of Optimus Prime that allows us to deal with the complexity. So for example, we decided that we wrap all the value types into the feature type, and then we identified three major types out of it. It's like a text, numeric, and collection, and we went forward with that. Despite that the hierarchy might look complex and it took us a while to figure out exactly the connections, and it actually doesn't contain everything. It's not exactly up to date, but it allows us to express ourselves better. I will show now some examples of that. So which leads us to this slide where I'm just showing how we get the type safety for value and feature operations when we deal with machine learning flows, especially for Spark. So we're currently aiming for Spark use cases, but it doesn't have to, like, don't think about Spark, right? Maybe think about pandas, like panda data frames, which are some metrics of data, right? Columns by rows. And so say I want to write a function tokenize for text. It's literally as simple as this. So I would maybe take text and then I would map over it and do some split and create a text list out of it. When I operate on the not on the value, but now, for example, on the whole column of the data, right? I don't know how many rows I have. I'm getting myself into a higher order type, such as feature, right? So we're going one level up. But we operate the same way as we do for the value types. So I would create a type of this, like feature builder.text with some extract function, and then say I want to tokenize, I would do title.map and then pass the tokenize function. So it actually gives us very good flexibility to express ourselves, as well as unit test all of the code that we built. Because the code doesn't really changes from the value to feature operations. It's all the same little functions, just need to correctly combine them. And then when we build a workflow, for example, in this case, which is just a set of stages of transformers or estimators that operate on the data, it's also very simple for us. So let me show you the actual example. This is the whole code you have to write. For example, if you would go and write a predictive application that would predict a book price. Let's imagine for a moment that you have a data set of books. And you have 4 fields in there: author, title, description, and price. And I would like to predict the price based on this three features such as author, title, and description. So I would go ahead and define the features from my data set. And then I might do some feature engineering on them. I would combine title and description together and we'll tokenize by removing some punctuation. And then naturally I might do some TF and IDF to get some popular tokens out of it. Then I combine it all together into vector type, right? Because we all have to get to some vector type to run any model on it, regression model. And after that, I spin Spark. So for example, the 2 lines of spin Spark, this is kind of essential for Spark. Whoever familiar with this is what you have to do. And then I would create a model selector that would go through possible model combinations and hyperparameter tuning phase, and will eventually speed up a good model for me, right? So there's like this train function at the end. That's what says, okay, now go run this thing. There is no mention of Spark constraints or cluster sizes or anything that is kind of quite a burden to write when you develop Spark code, for example. Or maybe when you develop in some other frameworks such as TensorFlow, you also need to remember to do some caching and like make sure some of the data is correctly cached so it will perform. There is no mention of the flow here. It's actually just a logic that you want to express. So there is like one magical shortcut here that I want to explore a little bit further. It's like a vectorize. It's like, what does it even mean to vectorize? So I take TF-IDF data and author data, which is a pick list in this case. Right? Pick list is like a set of values. What does it even mean to vectorize? What's the default behavior? So we built this vectorize because we know the domain of machine learning, and we took our best experience, best effort to try implement it. And this is what a lot of teams do as well, so just kind of to simplify the machine learning flows. What Vectorize might do? So depending on the type, it will apply a correct behavior for that type, which most of the machine learning engineers do, right? If we see a feature of type email, maybe we want to do top K domains from that email. Or if we see a phone number, we want to do phone number validation and then extract a country code because it gives us better predictive power rather than just a simple phone number value. Or if it's an age, such as like a numerical feature, right, we usually bucketize it. So why not do it automatically? And this is what we actually did. We went ahead and we automated a lot of those little pieces that kind of were repetitive across different applications all over again. So this is kind of things that you probably should keep in mind, is that your languages, your abstraction needs to be able to allow adding this functionality easier for your frameworks that you develop, because then you can just move faster with your application development. And for example, for zip code, I would like extract an income. Because it's by no means a full list, right? So much methods we can add into this framework to make sure that it becomes even more useful. So similarly, maybe in the scikit, right? I don't think it's too easy, for example, to extend scikit functionality, which I think is a failure of their library mainly. And for me as a software engineer, it's very important to make sure that we can add this functionality easily. OK, so after this Vectorize creates features for us, we actually need to do some automatic feature selection. So we want to analyze the features. This is also usually what happens in a proper machine learning application. We define features, we create them, and then we want to analyze them, compute some statistics and correlations between them, ensure that feature values fall into appropriate ranges. And is this feature a leaker, for example? Does it leak any information about the label? So it makes our model a weak model. So here's an example how you would do it, for example, in Optimus Prime. I would simply write price.check, which will apply the sanity check-in for the price label against the features. So price.check with a feature vector of features, and I will maybe send some instructions further for the code to do that, such as like sample limit and min-max correlation and so on. Another step that goes after feature selection is the model selection, right? We want to pick some algorithm that suits to our problem, and then run through the different hyperparameters for this algorithm, and make sure that we pick the best model against the test set. I don't know how many of you are familiar with Spark, but it's not that simple, for example, to do there. And for us, it's actually pretty trivial. Also, you can define it in a quite compact way. I would define a list of algorithms I want to run through, and for each algorithm, I would set multiple parameters to run through. And then, as a developer, I don't really care how it works. I just want to write it down. So this level of abstraction gives us this ability. And so this is actual slide from one of our applications of different algorithms that we ran. And it actually it matters a lot which algorithm you run against which data set. So here we compared like a random forest with gradient boosted trees, and like native Bayes, for example, which is like performed horribly on this data set. And usually people just pick one model that they're confident with. That they developed intuition. Well, they kind of think they developed intuition because we're really horrible to develop intuition, again, especially against statistical data. I would assure you most likely wrong when you think you developed anything on this. So you should delegate this precise work to compute to a machine, right? So this is why you should definitely build a proper model selector for your frameworks. I would like to show you a demo. Obviously, guess what? It's going to be about Titanic dataset. It's one of the most popular datasets out there. So can you see this? Yeah? OK. I will try to zoom in. So we've built a little command line tool for Optimus Prime that allows us to bootstrap projects faster. Because it's Scala, it's not super nice, especially for first-time users. So it's not like Python. You just open your editor and start typing. For Scala, you need to build like a project build and like put files in the proper folder and so on. So we built a little generator, but it's more than just project structure. It's also we're kind of trying to take in a data set. Let's see. We'll look on the passengers CSV file. So this is like a list of passengers on Titanic with their features. I would see their name and their age and which cabin they embarked and their gender. I would like to take in this data set and just generate some sane machine learning application that will do a prediction: did this person survive or not? So what I have to do is I will run the generator. So it takes an input, a CSV file. It takes the schema, which just maps which column, which name it has. It has an ID. I define the ID. OK, ID is a passenger. And then I'm going to call my project Titanic 1. So it just asks me, OK, what kind of problem is this? It's a binary classification, right? So it's like a survived or not. So that's it. So I get my project. I'll go to the project. I'll probably do clear, so we'll get to the app. And I'll just run just a regular Spark submit. I'll remove the quiet part, so we'll see it compiling. So what's going to happen now, it will compile the code, and I will do just a Spark submit, and it will run and train my model against the same data set I just gave it to it. Let's see what's going to happen. It's going to probably take a minute. So it's going to run, find some features, run some models, compare, maybe pick a random forest and logistic regression, and eventually, okay, done. And eventually what it's doing, it's actually writes out some results for me. So it wrote out that's okay, area under curve was 85, which is pretty decent just out of the box. And then the model type was RFC. This is random forest classifier. And then I might scroll up and see what does this model look like and which features were picked in. Right? It's like a survived, some vectorizer, name, sex, cabin, ticket, embarked, blah, blah, blah. So this is literally took me a couple of minutes. Right? Let's look on what this code looks like. I'm just going to open this project. Didn't work. Maybe because I have to reopen it. Yeah. I'll just close it. Let's see. Scala, okay, here we go. Whoa, didn't like this. I don't know what happened here. Yeah, maybe I'll just reopen this project. I don't know. Demos never go well as you would expect them to. You might know that. I don't know how to refresh this. I don't know. Looks good to me, but it's apparently not.
Delete idea.
I'll just do. That's a good try. Yeah, I actually didn't open it, so it's a fresh project, right? We just. Okay, let's do it from the beginning, because I actually want to show you some syntax coolness. Yeah, it's pretty fast to generate, so why wouldn't I regenerate it again? Okay. Okay. Oh, maybe this what was missing. Okay. Something. I think it's better now. Yeah, it's doing some syntax highlighting. Should do the, I guess, the presentation mode. Yeah, didn't exactly work. Let me hit the compile. Might generate. So because we use Avro here, right? The passenger type comes from Avro. Needs to be created by the plugin. So this is what my code gen created for me. For each feature, I have a handle, which is a val. It's typed, and then after we have this features here, I'll just keep scrolling, right? So this is basically all the features of my data set. Where is this being used? It's probably in a Titanic app. So this is just like a Spark app. And here I have some readers for the data. And what happens is it takes all the features and does the vectorize. And then maybe I have this label here. So it saved a lot of time for us to just all this hassle to write this code. But also now I can operate on the features. For example, say I have a name, right? So I have say, I'll do some, tokenized name dot. Yeah. Let's say I want to do map. I don't know what type is this. Let's say I want to create a text. Maybe I'll do text here, and maybe it's too complex for this IntelliJ to handle. I don't know what the hell. Anyway, believe me, it works most of the time. That's why I don't like showing demos. It's just never, almost never. But what I wanted to show is that it kind of pops up the operations you can do on the features. So let's see which type is this. Oh, it's a categorical feature. That's why. Okay, I see now. Let's take another one. Let's take age. Let's do age dot blah blah blah. So okay. So it's identified the type of the field as a categorical. So now let's say I transformed age to be a text now, and I want to do some stuff on the text. So I can do, for example, tokenize, and I maybe want to do like auto detect language true, and it will detect the language of the text and will try to tokenize it, for example. So this return features is exactly usable as other features, and I can pass it in through the Vectorize. The same pipeline will work. So, or maybe I want to do like TF, right? TF-IDF on this, and it's also very, very simple to write. And this one will return me a vector type. And moving down, right, we have some sanity check-in on the features, and then there's like a model selection here. Okay. Okay, back to this presentation. Okay. So how well does it work actually at Salesforce scale? It works pretty well. Most of the models that we currently deploy are completely hands-free. They're all auto-generated or partially auto-generated, maybe a little bit hand-tuned. Most of them are hands-free. They all train them like in complete automatic fashion. We currently serve close to 500 million predictions per day, and you can read about it in different block resources such as like TechCrunch and stuff. So what's your home takeaway from this? It's like a little recipe for you. Try to define appropriate level of abstraction for your machine learning pipelines, for your libraries of choice. If it's Scala, then great. You can maybe reach out to me, and we'll share some knowledge and some library from Optimus Prime, because we're currently doing open source pilot. So do that if you're interested in Spark and Scala, and use types. Definitely use types to express it. Like that's why they are built for. So they're really good for expressing any work for data and machine learning. Try to automate, because it saves your time and will save time for your teams, and it will definitely decrease the time that it takes from months to hours. So for further exploration, there was a talk yesterday by Carl, Skuch, and Jan about the real-time ML pipeline. So you probably want to look on the recording of that. It's going to talk about how we do real-time machine learning. And then there will be another talk later today, from Thomas Gerber on how we use Spark. There is a functional linear algebra in Scala today, also by Vlad Patrushev. It's a pretty interesting twist on how we do linear algebra in a functional way. There will be a talk of actually applying this little library that I just showed you for case classification and Einstein Builder tomorrow, and there will be some talk about DevOps if you're interested about that. How can we build an infrastructure to support this? We're obviously hiring, and thank you. Have questions? Yeah, we have time for questions if you like.
Any questions?
So I got two questions for you.
Yeah.
So one challenge that I run into in my team is most data scientists are more comfortable with Python than Scala. So are you guys running into some of this issue excluding a very Scala API? And my second question is, seems like you're using ML behind the scenes for machine learning.
Yeah, so the great question. So first question, in terms of using Spark versus Scala and like the friction between teams on using different languages. So we don't have that because we kind of say everyone use Scala and that's it. Like everyone has to, it's like it's a compromise, right? So everyone suffers a little bit. So use Scala and period, despite how nice Python might be, or kind of. So that's why we add features to Scala frameworks and Spark, which are missing maybe. To the second question is that, yes, we wrap around MLlib a lot because we don't want to rewrite, say, the TF-IDF transformer or word to vec or linear regression. We're currently exploring ways of doing scoring without Spark, and we're actually very successful on that. If you want to look, there is some Databricks advancement on that also. It's called, I think, DBML local. So you can look at inspiration of that from there. Yeah. But the idea is basically to export your model in some format that can be picked up by a different language, which is JSON. It's like simplest way, JSON with a bunch of arguments. And then you need to write an interpreter to perform the scoring of your model elsewhere. There is another one. I can recommend you looking into PFA. It's like a portable format for analytics. That's one that's a little bit more complicated. It's like a separate DSL in YAML/JSON that allows you to express transformers.
Am I planning to open source this then, or is it just maybe? Or?
Oh, it's not maybe. It's going to be open sourced. I announced it actually last year. We're actively working to open source it. Since it's the largest project we ever open sourced, we had to involve a lot of teams internally, like a ProdSec and so on. So it's happening. We're currently open for internal pilot. So if you're like interested, reach out to me, and then we can share the code with you before we open source. But we're planning to do that. Yeah.
Thanks.
Yeah.
Any other questions? All right, thanks, man.
Thanks.